Hi everyone. So now we are going to take a look at a program. So now we have fair understanding of how threads work and what are the issues with using thread. So we will see that. So we have a simple class over here that has a main function inside it. Now the program that I'm going to write is that program will first compute the sum of this list in a sequential fashion, and then it will compute it in a concurrent fashion. So you can see that we have a list of integers, and I have generated a random object because I want to populate it with some random integers. Okay, so that I have done here. So there are these many random integers inside this array for now. Okay. Now the first thing that I have done is I have written a method called as sequential sum. Now this method, all that it does is it writes a for loop and computes the sum of nums. So you can have a look at this. Let me navigate over there. So as you can see, this is our method and it simply iterates from starting index to the ending index and finds out the overall sum and then prints it. Okay. Just in order to do some profiling, I have captured the initial timestamp and final timestamp so that I can print out the overall runtime of it. Okay. Cool. Now you can see there is another method called as concurrent sum. Needless to say, the name itself explains that here it will find the sum in a concurrent fashion. Now I'll tell you the algorithm that I have used for concurrent summation. So all that I have done is I have partitioned this array into some parts, let's say 4 different parts, for example. Now each part will be allocated to a thread. So let's say the index 0 to index size by 4, where size denotes the size of array. The sum of that will be computed by thread 1. And then for the next segment, it will be computed by thread 2, then thread 3, and then thread 4. So now all these segments are independent. So their sums are also independent. So of course, threads can independently compute those sums. And then finally, we can add those sums to get the overall sum. This is the simple algorithm. So if you go to this method called as concurrent sum, you can clearly see here what I have done is I'm going to use 4 threads. So I have figured out the size of each of the chunk. Okay. And then I have created a thread T1. And then this thread is composed of a runnable. This worker class that you can see here is nothing but a runnable only. So it implements runnable, and all that it does is it takes the left and right index. So it takes the left and right index of the chunk which is allotted to it. Okay. And you can see inside the run method, what it is doing is it is initializing a local variable s, which is 0. And then it is iterating from L to R, figuring out the sum of that particular chunk. It is doing few more things over here. I'll talk about that in some time. So for now, let's head back to our actual class. Yeah. So you can see here that I have initialized thread 1, thread 2, thread 3, thread 4. I have just created these objects. I have still not launched these threads. Okay. You can see even the indexing that I have done is proper. By indexing, I mean I have assigned the left and right index of those chunks properly. And then finally, I have launched all the 4 threads. Okay. Now, you can see few things happening over here. The first thing is that when thread 1 is working in isolation, when you look at the workers run method, then what it is doing is it has created a local variable s, and then it is figuring out the sum from L to R inside this s, right? Now, each of those threads, thread 1, thread 2, thread 3, thread 4, will be independently doing these things. They will be having their own local variable s, which will contain the sum of the chunk that is assigned to them, right? But finally, we have to add those sums together so that we can get the overall sum correctly, right? So for that, of course, we need to have a shared variable, isn't it? Because if we don't have a shared variable, how will all these threads ever be able to add their contribution to it? They won't, right? So you can see that inside our actual class, I have created a static variable. It is a public static variable, so it is going to be global in nature, and it will be accessible to all the 4 different threads that I have created. The type of this is not a normal int or normal long. It is atomic long. Now, in the time to come, I'll explain what is this atomic long. For now, let's just take it for granted that I have created atomic long for some sort of safety mechanisms. But at the end of the day, what I want you guys to understand is that this sum for now is a shared variable. Okay. Similarly, there is another variable called as count. It is also a shared variable. I have initialized both of them to 0. Okay. Now, when you head back to your worker class, then you can see what we are doing over here is, after we have figured out this sum s, then the next thing we are doing is we are adding this s to this sum. This is all that we are doing, and it is important because each worker needs to add its contribution to sum, right? Okay, there is one more thing we are doing. We are incrementing the count. So if you do count dot increment and get, do you remember sum and count? They are not normal types, they are atomic types. So these atomic types have some methods like add and get, increment and get. So add and get takes a quantity and adds that quantity to this sum, and it also returns that value. So right now I don't need to catch hold of it. So I am not catching hold of that value. My major purpose to write this line is to actually add s inside sum. Similarly, my major purpose to do increment and get is to add 1 to this count. Now you may realize the reason I am doing this thing is because once a particular worker thread has finished its execution, has finished adding this quantity inside this sum, then it can do a count plus plus to denote that, yeah, this thread has done its job. So imagine, guys, we had 4 worker threads. By the time all those 4 worker threads would have executed their run method, what would have happened? The sum variable would finally contain the overall sum, and this count would have become equal to 4, which is equal to the number of threads. So if you head back to this main method, what would happen is that our main thread, after launching these 4 different threads, would get inside this while loop. When it gets inside this while loop, whenever main thread is scheduled, it would check what is the value of count. If it sees that the value of count is smaller than 4, it would keep looping again and again and again and again. This kind of thing is also called as busy waiting. It's a concept which you will see in the time to come, but we can actually see that main thread is waiting for the other threads to finish. And why this is busy waiting is because it is still consuming CPU cycles. Okay, you might guess at this point of time that this kind of busy waiting is not good because we are just wasting CPU cycles for a thread which is not doing any fruitful work. So that guess is right, but we'll talk about that in some time to come. But for now, you know that this main thread will keep waiting for count to become 4. And when count becomes 4, then this loop will be broken, and then finally this sum would be printed. Okay, at this point of time, I want you to understand one thing. Whether this code written by us is totally safe or not, whether this is free of all edge cases or not, I'm not going to talk about that right now. Through this example, I just want to show you how I had a need for creating 2 shared variables and how different threads were modifying them, and then main thread was waiting for a condition on one of them, which is count. Okay, cool. Now if you wish, you can just go ahead and run this particular program and see what happens. So a lot of you might be feeling that, hey, the concurrent sum will behave better and the concurrent sum will take a time which is going to be smaller. But guys, it might not always be right. Why it might not always be right? The first thing is that it totally depends upon how your threads are being scheduled and whether your machine that you have is a single core machine or multi-core machine, because the work that you are doing is still CPU intensive. So if you have a single core machine, you will not get any benefit. In fact, the performance would be worse, attributing it to the fact that there would be so many context switches and all such sorts of things, right? Okay, so keeping that in mind, what I would say is that when you run this program on a multi-core machine, most of the times you will see that concurrent things behave better than the sequential thing. Okay, so let's just go ahead and run our program. Okay, cool. So I just ran a program and you can see that the first thing I have done is I have printed the time taken by sequential execution. Sequential execution took 108 milliseconds and concurrent execution ended up taking 68 milliseconds. So yeah, it's smaller than that. And also we can see that the sums computed by both of them are exactly the same, and they should be, because if they are not same, that means something is wrong with our logic. Okay, so this was a very simple example where we ended up seeing that how concurrent codes can be written and how different threads can be made to work on some shared variables. Okay, now at times we end up seeing that the concurrent code is taking time which is more than the sequential code. Why that happens? That usually happens whenever there is contention for a shared resource. So like here, we all ended up seeing that this sum variable was a shared resource, right? Now, if I take you back to the worker, what we were doing, we had first created a local variable inside every thread, and then each thread was modifying this local variable only, right? And finally, they were adding this s inside this shared variable, which is math.sum. But guys, what if I do not create this? And what if instead of doing something like this, every time I add value inside shared variable only? So in that case, the code would start looking something like this. This is what you will have. And now I am just going to remove this. So do you see the difference? The difference is that previously each thread was computing the sum inside its respective local variable and then was finally adding that local variable to the sum, which was global. But now it is directly adding all the values to the global variable only. So what do you think? Is this functionally correct or not? The answer is yes, it is still functionally correct. But will its performance be better or will it be worse? Just pause and think. So guys, we can already see that there are going to be so many contentions for this global variable. This global variable is a shared resource, and while it will be accessed by thread 1, other threads will have to wait. Similarly, while it is accessed by thread 3, other threads will have to wait. So there will be too much of contention, and in this contention process, the other threads will have to spend a lot of time staying blocked or staying waiting for that shared resource to be freed. So if I rerun this program, then you can see there is a drastic difference in the runtime that has come. Okay guys, so a lot of things have been conveyed in this class. But the important thing that I wanted to illustrate was that how different threads can actually work on shared variables. And while they work on shared variables, there are contentions to acquire those shared variables and make changes on them. And because of those contentions, it can happen that your concurrent code ends up taking much more time. But yes, there are ways to optimize that contention. So our initial code had optimized that contention, right? So in the time to come, we will hear about many other ways of doing so. Stay tuned.